let's explore the algebraic properties of row vector matrix multiplication. This has three different flavors. The first one we'll call distributivity, which is if we sum two row vectors and then multiply by a matrix, that's the same as multiplying each row vector by the matrix and then adding that sum. The next one is called scalar multiplication, which is we can bring scalars out of matrix vector multiplication. So if the first thing I do is I multiply a scalar by a row vector, and then I take the product and multiply that by the matrix A, that's the same thing as taking the row vector, multiplying it by A, and then finally multiplying by the scalar. In other words, the scalar pulls out. The third one is called linearity, which is actually a combination of these two. If I take any linear combination of two row vectors and then multiply that by a matrix, that's the same thing as taking a linear combination of the output of the products of each row vector individually. If you remember back to a previous video, we actually explored these same algebraic properties for matrix column vector multiplication. And in that video, we actually went through a proof of distributivity and scalar multiplication using the linear combination and dot product versions of the matrix vector multiply operation. In this video, we're going to develop yet another way to think about how to establish these. And in particular, we're going to focus on the third property, which is linearity. Before we dive into the formal study of these algebraic properties, I wanted to highlight kind of a metacognitive approach to what we're doing as we build this knowledge. Specifically, if we look at a blog post that I wrote called Progress Through the 5 Stages of Deep Learning, I want to highlight one of the approaches that we're taking here. I like to say that deep mastery in mathematics is a process, not a destination. And specifically, I like to encourage my students to think about 5 different steps, moving from unconscious inexperience, you have no experience with or even know about a particular idea, all the way through master learner, which is best summed up by the motto, those who can do, those who teach do better. When I'm working with students who are new to a subject, like if you're in this class, you probably have never taken linear algebra before, I like to shoot for what I call conscious expertise. In other words, you develop a deep conceptual framework and understanding for the topics that you're studying. To do this, I like to actually seek out multiple representations for any single math idea. I break these into levels. So I like to say that a student that has conscious expertise in a math class has really put together a neural network that encodes one idea with multiple different perspectives. So at the beginner level, in order to reach conscious expertise, I like to use the VANVISA. So V means verbal descriptions, and there's 2 types of those. Abuelita, intuitive language, and also nerdy formal language. I also like to encourage my students to really get excited about inquiry and intrigue. If you're ever studying math and you start to have questions, my claim is that those questions lead to deep explorations, and that's something that we should really treasure like gold. Also, symbolic representations, which is symbols written on a page. We already see those here. They're provided for us. That doesn't mean we understand them, right? So we have to be able to capture those single symbols in our own mind. And then also algorithmic calculations, being able to do, where appropriate, procedural mathematics. So that's what I call the beginning level. The intermediate and advanced level are really transitioning from conscious expertise all the way to master learner and to be able to make money using math is a fast way to say this. As we're working on this particular study of algebraic properties of row vectors, we're actually going to dip into many of the beginning levels and also thinking about the logical construction. So we're starting to get to the intermediate level of mastery as we dive in here. With that in mind, let's break down this theorem statement and think about the logical constructions underneath. Remember that anytime we're analyzing a mathematical theorem, it's really helpful to restate our theorem using a conditional statement. This is a formal logical structure that allows us to break down what a theorem is saying. In this conditional statement, we read this as P implies Q, and that is a double arrow, so it's 2 parallel lines with an arrowhead. The P statement is called the antecedent, the Q statement is called the consequence, and we read that as if P, then Q. It's at this point that I like to say a best practice for learning math is that every time you're learning a theorem that is new to you, rewrite the theorem in your own handwriting and translate each claim made in the theorem statement into the conditional statement P implies Q, where you're explicitly identifying the antecedents P for each consequent that is given in the theorem. This takes some practice to do well, and I'm going to claim that I actually see 3 separate theorems with 3 different sets of P and Q statements in this theorem statement. Let me show you what I mean by that. Let's look at the first proposition. Here, the proposition associated with distributivity is actually if A is an m by n matrix and x and y are m by 1 column vectors, then it is true that x plus y transpose multiplied by A is equal to x transpose times A plus y transpose times A. In other words, here is the antecedents, here's a consequence associated with distributivity. Let's look at the next proposition down. So for scalar multiplication, we have a different set of antecedents. If A is an element of R m by n, x is an m by 1 column vector, and alpha is a real number, then scalar multiplication tells me that alpha times x transpose times A is equal to alpha times quantity x transpose times A. In other words, I can bring out that alpha. And yet a third proposition states that if A is an m by n matrix and x and y are m by 1 column vectors with scalars alpha and beta, element of the real numbers, then linearity claims that if I take the linear combination alpha x plus beta y transpose multiplied by A, that's the same thing as bringing the alpha and beta out as well as the addition. So that's alpha x transpose A plus beta y transpose A. Notice that what we've done is we've broken down a very complex theorem into individual parts, each of which has that structure if P then Q, and we've explicitly identified the antecedents and consequence of each statement. In our previous videos on the algebraic properties of matrix column vector multiplication, we actually showed how to prove the corresponding algebraic property using two different methods. One method was using the definition of matrix column vector multiplication via linear combinations, and the other one used the definition of matrix column vector multiplication using dot products. We could extend those results in this particular exploration to show the same processes are applicable for row vector matrix multiplication. However, in this video, I want to add some new insights about developing a general proof to these propositions. In particular, I want to make a conjecture that actually when we look at these three different algebraic properties, two of them are equivalent to the third one. In particular, if I know that row vector matrix multiplication satisfies both distributivity and scalar multiplication, then I actually get linearity for free. And the reverse is also true. If I know that row vector matrix multiplication satisfies linearity, then distributivity and scalar multiplication fall out of that. In other words, there's an equivalence. Do you see the P implies Q structure? Now, as a mathematician, I recognize that once I have these two statements, I can actually combine those into a biconditional statement, two-directional conditional statement, which is distributivity and scalar multiplication is equivalent to linearity. The intuition that I'm using here is that when I look at linearity, check out that I have an alpha x plus beta y. Well, the addition, I could just think about this as a vector and that's a vector, so I'm back in this case, which means I could break up, if I know that it's distributive, I could break up this addition into the addition of the outputs. And then if I have scalar multiplication, I know that I could bring out this scalar for one of them and a scalar beta for the other one, which means I get linearity for free. And the reverse is also true. Assume that beta is 0 and alpha is any scalar, I get scalar multiplication. Or assume that alpha is 1 and beta is 1, I get distributivity. That's the intuition there. With that, let's get more practice translating our intuition in mathematics into formal logical structures. So our intuitive draft is going to say, if distributivity and scalar multiplication hold, then linearity must hold. This is intuitive language. Let's formalize it with a technical draft, which says that if I have an m by n matrix, and then two column vectors, x and y, with m rows and 1 columns, and scalars alpha and beta, and I know that row vector matrix multiplication satisfies distributivity and scalar multiplication, I'm going to make a claim that it must be the case that alpha x plus beta y transpose times A is equal to alpha x transpose times A plus beta y transpose times A. In other words, if these two things are true, linearity must be true. What we're going to do for the rest of this video is actually walk through how we might actually establish this. And for those of you math heads that get really excited about formal mathematics, I cannot recommend this book enough, How to Read and Do Proofs. It's by Daniel Solow. Remember, when we try to prove a P implies Q statement using a direct proof mechanism, what we're going to do is assume the antecedent P is true and then show that the consequent must also be true from that. For this discussion, let's use the forward approach to establishing the consequent. Specifically, what we'll do is we'll break the consequent into two different pieces. So we have expression 1 and we want to show that's equal to expression 2. What we do in the forward approach is we start with expression 1 and then use any knowledge of definitions, theorems, anything that we've studied in the class, plus the assumption of the antecedent that we started with for the proof, so that we can get towards expression 2. So we're working from expression 1 forwards to expression 2, where the forward direction is because we read from left to right. Okay, with that, let's go ahead and assume that the antecedent is true. So we say that A is an m by n matrix. We have 2 column vectors with m rows, identical to the number of rows in A, and then we have 2 scalars, alpha and beta. We also suppose that we have distributivity and scalar multiplication. And then what we want to do is start with expression 1 and move forward. So we're going to say, let's consider alpha x plus beta y transpose multiplied by A. One inquiry question we can ask ourselves is, how is this statement related to one of the antecedents or something else that we know about this type of operation? What I might say is that the first thing that we can do is actually think about alpha x as a vector in its own right, and also beta y. So here, alpha x is playing the role of vector x, and beta y is playing the role of vector y. What we know that if we just take a vector sum inside the transpose, distributivity tells us that we can actually separate those into 2, which means that I could look at this as just a vector, and this is a vector, and I can separate it via distributivity, which is I've assumed to be true in my antecedents. So this now becomes alpha x transpose multiplied by A plus beta y transpose multiplied by A. But I also have scalar multiplication, which I've assumed to be true in my antecedent, which means that I can pull out the alpha from the first one, and I can pull out the beta from the second one, and now I get alpha x transpose A plus beta y transpose A. That was exactly expression 2 from the consequent that I wanted to show. In other words, we've shown that if we have distributivity and scalar multiplication, we must get linearity for free. Let's try the other direction to get more practice. In other words, we've just shown that distributivity and scalar multiplication give linearity. Can we show that linearity implies distributivity and linearity implies scalar multiplication? This would be a great place to pause this video and try for yourself. I'm going to actually walk you through that. So go ahead and pause, give a try, and then we'll do it together. The first thing that we'll do is we'll translate our intuitive version of this proposition into a technical version. So specifically, let's look at if linearity then distributivity. So if it's true that linearity holds, in other words, I have a m by n matrix, 2 vectors, and 2 scalars, and alpha x plus beta y transpose A is equal to alpha x transpose times A plus beta y transpose times A, then it must be the case that x plus y transpose times A actually breaks into 2. I must have distributivity. That's that first statement. Let's break the second statement down using a technical version. So specifically, we're going to say, if linearity holds, if it's true that my row vector matrix multiplication operation is linear, then it must be the case that it also satisfies the scalar multiplication operation where I can pull the alpha outside the product. We'll begin with the first proof. Remember that in order to do a direct proof of a P implies Q statement, what we do is assume the antecedent P is true and then work towards the consequent using any of the antecedents that we've assumed plus any knowledge that we have related to the structure of the consequent. So here we assume that row vector matrix multiplication satisfies the linearity condition. And in this case, let's actually use a backwards approach where we take the right expression in our distributivity and then work backwards for the left expression. So specifically, let's consider x transpose times A plus y transpose times A. We know in this situation that we can always think about a invisible 1 sitting outside of that as a scalar. So now I have scalar 1 times this product plus 1 times that product. But we might as well think about this as alpha times x transpose A plus beta times x transpose A, where alpha and beta are both 1. This was true for any scalars. It must also be true for the scalars that are equal to 1. But once I have it in this form, that's the expression 2 in my linearity condition, which means I can go back towards expression 1 since I've assumed linearity to be true. But I know this is true specifically for alpha equal 1 and beta equal 1, which means that I get x plus y transpose times A must be equal to x transpose times A plus y transpose times A. That's exactly what I wanted to show. Notice in this case, we decided to go backwards rather than forwards because why not, right? We're kind of strutting our stuff, doing some sea walking here. All right, let's move on to the next one. Let's prove that linearity is equivalent to scalar multiplication. So we assume the consequent. We assume that our row vector matrix multiplication is linear, so it satisfies this condition. And then let's do the forward approach here. So we'll start with alpha x transpose times A. And remember, we want to show that the consequent is true, that I can pull the alpha out. Let's think about what we know. Well, we know that alpha x transpose times A is equivalent to alpha x plus 0 times y transpose. Because 0 times y is just 0, it disappears. I can always bring that back in. That's the mathematician's favorite trick, right? But I can contextualize this using linearity. 0 is just one form of scalar beta, this was true for all possible betas. It was true for any real numbers. So it has to be true for beta equals 0, right? Which means we can apply linearity to break those into 2. And then once we've done that, we remember that beta was 0, which means this disappears, which means we get that scalar multiplication consequent for free just by breaking it through linearity. What we've just done is shown that distributivity and scalar multiplication are equivalent to linearity, which means if we can show linearity, we get the other two for free, or vice versa. Since we've already seen how to do this for specific examples in our previous video, let's actually develop a general proof of linearity in this example using the linear combination version of row vector matrix multiplication. To do this general proof of linearity, we're going to assume the antecedents are true and show the consequence. In other words, we're going to assume that A is an m by n matrix. We have 2 column vectors of the appropriate size, and we have 2 individual scalars. And we'll bring in our proof in a forward direction. So we'll consider the expression 1 in the left-hand side of the consequence, and then work towards expression 2 and get as far as we can. And if we get stuck, maybe we'll try the backward direction. So with that, let's take a look at expression 1, alpha x plus beta y transpose times A. We actually know what those look like in general. We know that x was m by 1 and y was m by 1 and a was m by n. So we can actually think about the scalar versions of those. We know what scalar vector multiplication does. Specifically, when we take a scalar multiplied by a vector, we bring that scalar into each individual entry. And the same thing is true over here. We bring beta into each individual entry. But when we're looking at this, we also know what vector-vector addition does. We can just add the individual entries. So now we have this sum of individual entries, the entire vector transpose. And then remember, this is row vector matrix multiplication, and we're doing it via linear combinations, which means we're thinking about this as the algebraic worker, and we're thinking about this as our modeling matrix. In the linear combination versions, we partition the modeling matrix into rows, and then we scale each row by the appropriate entry from the vector on the left-hand side, creating a linear combination of the rows of our matrix with scalar multiples coming from the individual entries of our vector. This moment, let's go ahead and explicitly take the transpose there. So now I have a row vector where each individual entry is given by the sums that we have there. And here are my rows. So what I'm going to do is pair this individual entry with row 1, add that to the next entry to row 2, and I go all the way down to the last row m, and I multiply that row by the last scalar in my row vector. And then I take the sum of those. I'm going to immediately jump to the summation notation just to save a little bit of space on my paper. If I wasn't used to that, I would actually write out each individually, because the point of this is not to do the proof fast. It's to create robust neural networks that encode these ideas and really give us training with the definitions that we've used. Now that we're looking at this, let's pretend that we didn't know what to do from here. Let's imagine that we're stuck. We're working through this proof and we're like, I don't really know what to go from here. This is exactly where we might want to pull out the backward direction. When generating proofs using the backward approach, instead of starting with expression 1 and moving forward to the right towards expression 2, what we do is we start with expression 2 and see if we can move back towards expression 1. The hope is if we combine the forward and backwards approach together, we might actually be able to converge in the middle with a lot less pain and suffering. So with that, let's start with expression 2. Here I've got alpha times x transpose A plus beta y transpose A. I'm just literally copying down what expression 2 is. Let's actually look at the entry by entry approach. I know what x looks like. I know that I'm doing the linear combination of row vector matrix multiplication, so I'm going to partition my matrix into row vectors. This is one of the major takeaways of this lesson. When I multiply a row vector on the left by a matrix on the right, and I want to do it using linear combination, I chop the matrix into row vectors and then scale each row vector by the appropriate entry of the vector on the left. So this is going to be the sum from I goes from 1 to m of x sub I multiplied by the ith row vector. And the same thing over here, when I multiply y transpose times A, that's going to be the sum from I goes from 1 to m of y sub I multiplied by the ith row vector of A. But notice that each of those sums is a linear combination of row vectors, and on the outside, all I'm doing is multiplying by a scalar multiplication, which means I could actually bring that scalar multiplication inside. So this is alpha x1 times the first row of A, alpha x2 times the second row of A, all the way down to alpha xm times the nth row of A. And then over on the other side, we've got beta y1 times the first row, beta y2 times the second row, all the way down to beta ym times the third row. So check it out. We've gone the forward direction and got to this point. We got the backward direction and got to that point. We might ask ourselves, well, what are the connection between the two of those? To make that connection explicit, let's actually unpack the summation and write the individual scalars. So notice that for each of those, I goes to 1, this is going to be alpha x1 plus beta y1 times the first row, I can distribute this through because that's just scalar addition over scalar row vector multiplication. So I can just pass one of those scalars to each of those. So now I get alpha x1 first row of A plus beta y1 second row of A. I do that m times. I do that for the second one, alpha x2 second row plus beta y2 second row, all the way down to the last one, alpha xm mth row plus beta x ym mth row. But now when I compare this to my backward direction, we notice that the only difference is that here, all the terms that involve alpha are grouped together, and over here, all the terms that involve beta are grouped together. And we might ask ourselves, well, can we do that? The answer to that question is, of course, yes, we can. Vector-vector addition is what we call commutative. I can do vector-vector addition in any order. In other words, I can reorder these to group all the alpha terms together and all the beta terms together, and that's exactly what we want. So now if I look at the two directions of my proof, I've actually finished this in the general case. So we've established linearity, which means we've established both distributivity and scalar multiplication for free from that, and we did it in a completely general approach. That brings us to the community challenge for this video. What we've done in this work is show that linearity is equivalent to distributivity and scalar multiplication. And then what we did is show linearity using the linear combination version of row vector matrix multiplication. Community challenge, go ahead and prove linearity using the dot product version of row vector matrix multiplication. So come up with a different proof of the same idea that we just did. With that, we end this video. Thank you so much for your attention. I'll see you in the next video where we explore the connection between matrix partitions and the different versions of matrix vector multiplication that we've studied in this lesson. See you there.